Welcome back to another video on speech processing. In this case, we're going to look at speech synthesis. That is text-to-speech concepts and some software demos as well, called speech synthesis or speech generation, text-to-speech, various names. Right. The task is to generate spoken human language from a text, right? And there's some issues, like anyone in particular. Are we trying to imitate some specific voice of a person? What training data do we have to create this, to do this? Which approach and why? And are there any ethical challenges? Do we want to try and imitate someone else's sound? The challenge is that humans are good at identifying non-human speech. And there's this idea of the uncanny valley. Let's take a look at that real quick. Here's a Wikipedia article about that. In aesthetics, the uncanny valley is a hypothesized relation between a subject's degree of resemblance to a human being and the emotional response to the object. The concept suggests that humanoid, that is human-like objects that imperfectly resemble actual human beings provoke uncanny or strangely familiar feelings of uneasiness and revulsion in observers. Valley denotes a dip in the human observer's affinity for the replica, a relation that otherwise increases with the replica's human likeness. So like on the right-hand side of this article, we have this plot where we have familiarity on the y-axis, and we have human likeness on the x-axis. And it increases, but then there's this point where like it's too human and it's really uneasy or like really revolting to have something so human-like. That's the uncanny valley right there. That's what that refers to. Okay. State of the art, dozens of commercially available systems, many systems available. This research has been going on for decades, like all the way back to like 1939. There are dozens of open source research platforms as well as commercial subscription services. There are standalone systems as well as those that are used in a pipeline of some sort. Here's a Wikipedia article about a comparison of speech synthesizers. Amazon Poly there, AT&T, eSpeak. That's what Pratt uses under the hood to do its text-to-speech. I'll just say TTS for text-to-speech or speech synthesis. Anyway, you can take a look at this article. There's some technical information, details about this. I'll let you guys look at that. Okay, good. Speech production conceptualization. Well, let's think about how we generate speech in we humans generate speech, right? We have some message form in our mind. There's a formulation of a message in our mind. Then we go to encode it in language, whether our first language or our second language, right? And then we have neuromuscular actions or gestures that we have to figure out. And anyone who has learned a second language and has had to learn different sounds or different phonotactic patterns knows just how tough it can be to get the neuromuscular gestures correct. It takes practice, right? It's a learned skill, not just declarative knowledge. It's a procedural knowledge thing. And then we have a sound source, right? It goes into an acoustic system and it actually produces a sound wave that goes to the air, to our listener's inner ear, right? That's how speech happens in humans. With text-to-speech, it's not a whole lot too different. I mean, it's similar but different, obviously. We have input text that gets tokenized of some sort and normalized. And then we do syntactic parsing. And we access a pronunciation dictionary to get the phones or the phonemes that need to go into it, right? Some grapheme to phoneme, letter to sound thing. And then we need some prosodic rules, right? Prosody is a big part of speech. That is intonation and duration of certain sounds and shortening of other sounds, right? Articulatory motion and waveform generator, and then the sound wave is actually produced by the system. So similar and different. Here's a graphic of components of a TTS system. Right, we have the input sentence coming in here. We do text processing. We have a phoneme sequence that goes into the acoustic synthesizer. We also have this prosodic control that influences how those phones should be pronounced, the duration rules, pause, etc. Here's an overview of the bottom part of this slide. Looks at an overview of another system, right? Text coming in from the left, text analysis, utterance composed of words. We have phrasing, intonation, duration, these linguistic the linguistic analysis right there. And then the utters is composed of phones, and that goes into a waveform generator, and that comes out as speech. Okay, so why text processing? Well, homographs are rampant in English. That is, words that are spelled the same but pronounced differently, right? For example, my cat who lives dangerously had 9 lives. Those 2 underlying words, lives, lives, are spelled the same but have different pronunciations. So having a TTS system get those correct, that is lives and lives as different things, right, is important. How also this second sub-bullet on this first main bullet here, right? Henry V, Part 1, Act 2, Scene 11, Mr. X. Right, so right here, XI is 11, but here it's X. Anyway, dealing with abbreviations and letters like this is an important part of getting a text-to-speech system working correctly. Also, punctuation conveys more than we imagine in speech. So here's an example. Constituent boundaries interact with prosody. So for this first sentence, he wanted to opt in for a drive-in. He wanted to opt in for a drive-in. Versus the second one, he wanted to opt in for a drive in the country. In the country, right, is that prepositional phrase, whereas a drive-in, there's less emphasis on that in there, but more so on this drive in the country. So the point is that this punctuation in writing has an effect on prosody in speech that we may not be aware of when we are just reading that and not saying it out loud, or even if we say it out loud, we may not realize that those have different prosodic contours. There's also domain-specific prosody, zip codes and phone numbers and street addresses. Like, you know, if you're reading out this contact information, the way you say a phone number, right? 817-839-3689. There's a pause, at least when I say it, between the last 2 digits right there in the previous 2, right? So that kind of effect is the way things like that are read. There's a funny episode of what TV show was it? I can't remember the name of it. Anyway, the father of the protagonist said something like 16, and then like pause, and so the son wrote 16, but it was like 1600, and so he had to like insert something like, that's not the exact example, but something like that, where the prosody of how you say something can affect the writing and vice versa. Also, intonational focus, right, to emphasize certain things like yesterday was sunny, but it will be rainy today in Boston, in contrast to like sunny yesterday. Or here's another example: it will be rainy today in Boston rather than yesterday. Or it will be rainy in Boston, right, rather than New York City. So again, obviously using intonational focus is an important part of speech, and that needs to be considered with TTS systems. Okay. Here's a nice webpage on TTS examples with some older examples. Excuse me. Let me just play a few. This is from a while back, you can see, but here's some.
This is a short introduction to the festival speech synthesis.
Anyway, pretty old examples at this point, right? Just very robotic. But take a look at that webpage and just listen to a couple examples from a couple decades ago. Basic approaches. You can have articulatory synthesizers that model and simulate all pertinent aspects of the human vocal apparatus. That is the vocal, lungs, throat, mouth, and nose, and tongue, and teeth, that are trying to mimic physiology and acoustics and neuromuscular physics. These are not very common in industry because they're very costly. Concatenative synthesizers compute linguistic units and selects corresponding speech segment recordings, and then tries to smooth the transitions between those and concatenates them all together into the utterance. Formant synthesizers are kind of a combination of the previous two, where they model the main features, but not the articulatory apparatus, but rather of the properties of the speech signal. And so you have phonation as well as filter. If you remember, we talked about with phonetics, air coming out of our lungs goes through our throat and our mouth and our nose, right? And the throat and the mouth and the nose are kind of like this filter that adds harmonics or formants that creates the tones that we need, the sounds that we need. Okay, and Pratt has the ability to do all three of these speech synthesizers. So let's look at units of speech synthesis. This is relevant for both TTS as well as ASR systems. How to, with ASR, parse down a speech signal into its component parts and get it into a text. The other way around, if we have text, we want to go out to speech, right? Figuring out what units we need is important. So concatenation is a common technique, right? You store some audio recordings of pieces of speech and then splice them or concatenate them together. Again, trying to smooth out the transitions. But what should you concatenate? If we were to go at the word level, we would have to have a recording of every last word, for example, in English, every last word in English. I don't know how many words are there in English? Hundreds of thousands of words, word tokens, right? Word types in English. So that's not really practical, right? Because, it's not practical. The phoneme level is probably too small because the transitions will get really messy, really hard to make it sound natural if you're just having one phone at a time. And so a better option is to do diphones or demisyllables. Diphones are two phones, the di, right? Two phones there. So on the bottom part of this slide, we see a word segmentation right here, the word segmentation. And then we have the phone level. We have each phoneme right there in the second tier. And then the third is the diphone, where we have two phones together recorded. And this is not too bad. There's probably maybe 1,000 diphones in English, right? The phonetics of English allow for approximately 1,000 diphones. So that's not too bad to get 1,000 recordings that you then concatenate together and manipulate prosody as needed. The syllable perhaps is still too big, but a demisyllable is when you take a syllable and slice it in half right at the nucleus. You have the first part of the syllable and the second part of the syllable. And so that's another better way than the full syllable. And there aren't too many demisyllables to make that impossible. Okay. Modeling speech and articulation. Well, yeah, prosody, like I mentioned, is an important part of speech, a super segmented part of speech that we often take for granted as humans speaking, but trying to create a system that can approximate human speech needs to involve prosody. Right, that deals with rhythm and tempo and accent, intonation, stress, and prosodic phrasing and emphasis, like we talked about with Boston, rainy today. Okay, so we have syllable, subset duration, speech rate, and dialect and emotions, gender. Right, all that should go into a TTS system. Phonological processes and cliticization, like rather than saying I am Earl Brown, I'd probably just say I'm Earl Brown. I'm talking to someone, informally at the Cougar Eat, right? I'm going to say I'm Earl Brown. Who are you? Rather than I am Earl Brown. So dealing with that type of reality of speech is important as well. And the oscillators, the vocal folds, and what happens with the physiology of human beings when they speak and what happens and the effect that physiology has on speech should be tried to be approximated in TTS systems. Obviously, the earliest TTS systems didn't do a good job. They sound very robotic, very non-human. The current state-of-the-art systems are really good, like really approximating human speech really good. And they're doing a better job with dealing with the things that humans deal with in their speech, right? Pitch and glides and creakiness and vibrato, breathiness. I'll show you an example here in a minute where it's a TTS system that takes a breath and does like a filled pause as well. Other factors include voice, like genetics and development and aging. Older speakers will have, you can kind of tell an older person's voice than a younger person's voice, even if they're both adults, right? The younger person's still an adult. Right, disease, emotion, like I mentioned, the environment, coldness can affect your voice, or getting over a cold, an illness. So all sorts of things happen with human speech, and trying to simulate that in a TTS system is important. Also, markup is an important part of TTS systems, some TTS systems, where you can put in things that you want to be emphasized, or you want a break here, or you want some pitch to go up here or down here, or you want it to be louder. So here's some examples. Let me see. Let's look at this real quick. This is this Sable markup language. This is a collaboration between Sun, AT&T, Bell Labs, Edinburgh, and CMU, University of Edinburgh, and Carnegie Mellon University in Pittsburgh, Pennsylvania. Anyway, you can see that they have different tags in their XML markup language to indicate certain things like take a breath here, break here, right? And I have an example on the slide itself. The top right of this slide, you can see that here's an emphasis tag around big. So this is a big car. And then you can also put an attribute in that tag, emphasis level equals strong. This is a huge, just really a bigger emphasis, a stronger emphasis there. So that's an important part of some TTS systems, is this XML markup language where you can put in different aspects of human speech. Right, slowness. I'll show you an example of slowness, saying something slowly. All sorts of things happen in human speech, and trying to model them in a TTS system can happen with XML markup language like this. Synthesizing more than speech. The more information, the better, up to a limit perhaps. So when you have an animated agent talking head, like a virtual humanoid example, I have an example here. You want it to look human, but again, we have that uncanny valley thing where if it's like too human-like, it's kind of weird for humans, like, is this a human or not? It kind of like causes uneasiness. So here's an example of a humanoid. Let me just stop real quick. This is an advertisement for a PhD position in conversational speech synthesis at a university in Sweden, one of the best universities, technical universities in Europe. And just watch this.
We have a PhD position in conversational speech synthesis for collaborative robots. We will develop robots that can help humans in domestic settings by performing simple physical tasks. The overall goal is to design robot behaviors that are perceived as safe and, more importantly, that are socially accepted. We will develop a conversational speech generation system that can change its way of speaking in order to convey the robot's mental state and verbal capabilities. We think that this will make the robot more useful and entertaining to interact with. Our robots are to be able to speak with male voices, or of course with female voices, and why not with a voice that combines both genders. So if you want to be part of our team, please apply for this position at the KTH webpage.
So it's interesting that you can see that there's blinking, eye blinking, head movement, kind of occasional eye gaze up to the top left or top right or something, like what humans do, right? If I were to talk straight into the camera, never blink, never really move, never look away, it'd be weird. You'd be like, whoa. So taking that into account when you're creating a humanoid agent and using text-to-speech, creating a text-to-speech system to go with the humanoid agent is important, right? And so correlating body movements with speech is important, right? We saw the eyebrows and obviously the mouth and the lips, teeth being exposed, visible sometimes. Emotion. I don't know if you heard the agent did like a filled pause at one point and had pauses, right? It wasn't just one continuous speech stream. Okay, blinking and closed mouth breathing. So morphing between facial configurations. This is an important part of trying to create like I just said, a humanoid system. You'll see in cartoons, right here I have an example of this cartoon where there's only three or four different mouth positions of this Baffy position, or like a cartoon position named after an early cartoon.
Everybody wants to come in on top. That's whether it's the Super Bowl. There's nothing like being the greatest ever. So right now, I want to talk to you about someone who is considered one of the greatest of all time.
You can see that it's just there's only like 3 or 4 different positions for the mouth. Anyway, or you can get more positions, right? Having 10 different mouth positions and 4 different eyelid positions, half open, open, way open, or closed. So taking all this into account, it creates a good TTS system that, in this case, goes with some visual cue, like a video or a humanoid agent. Okay, but you also want some transitions. So not just momentary snapshots like with that cartoon we just saw. There's like just simply crisp and hard transitions, just going from one position of the mouth to the next. We want to have some transitions or trajectories between them, like in that first video for that PhD position in Sweden. There was a lot of transition and movements. Wasn't just like the cartoon with only a few mouth positions. Okay. Voice conversion or voice cloning, right? You could record someone's speech and modify it so that it is used with someone else's a video of someone else, right? So that there's some ethical considerations, right? Do you want to try and get the voice quality of someone else and use it to have them supposedly say something else, right? There can be ethical considerations of that, but that's a thing. NTTS is cloning a voice, so you can have you can use the voice of someone else to say certain things. Again, there's some serious ethical considerations to think about with that. But that can be done with dubbing or morpheme, right? Dubbing video movies to use the actor's voice in a different language, for example. Okay. Anyway, I have a graphic here on the right side of this slide here about this. We have the source speaker and the target speaker, and we do speech analysis, pull out speech features, mapping the feature computation, and mapping the features together, and we end up with basically cloning someone else's voice. Machine learning for refining output. We want to categorize basic text-based issues, so intonation and prosody. And how can a machine learn that? Well, we can with training data, right? That's how machine learning happens, with a lot of training data. And so let me remove myself. Let's see how I can remove myself real quick. Go to this view. Lots of annotated data. So on the bottom right of the screen, we have a text grid and a waveform and spectrogram from Pratt, right? We have the waveform on the first tier and the spectrogram on the second tier. And then on the third tier, which actually has a number 1 on the left-hand side, is the TOBE, which is tones and break indices, notation of pitch to annotate pitch. So we have low and high values and breaks and pauses noted there. And then on the second tier down, what's labeled as number 2 tier, in the bottom part of the screen, we have the words and silence noted as well. And 3 and 4 down at the bottom are other things, breaks and miscellaneous information. So given enough of this type of stuff, we could put this into a machine learning system and have it learn prosody and intonation based on previously annotated intonation contours with the TOBE system. Again, with enough examples, you need a lot of examples to have it do a good job. Okay. So let me put myself back here. To do, well, you should take some time to explore some of these examples. Here's an excellent historical overview of TTS systems. Let's take a look at some of these. Some of these are astounding. The CLAT record. So this came on a record, an actual LP record from 87. You can see here's an example from 1939. Let me just play this. If you click on it, it'll download an AU, which I already have. Let me just play part 1 for my downloads. Let me come over here, and you can see what I'm doing if I bring it over here. So downloads A1, part 1. Listen to this. If I can get it up. That's over in Pratt right now. 1 second, I got it over here. Let me bring Pratt over to this screen. Part 1, here we go. Let's listen to this.
1. The Voter of Homer Dudley, 1939.
Will you please make the voter say for our Eastern listeners, good evening, radio audience.
So that was from 1939. That's like, I mean, that's very robotic and very not state of the art, obviously. But for 1939, that's not horrible. I was surprised to hear how good it did from 1939. Let's look at a couple more, actually. Let me go back to this point. Let's jump down a little bit. Let's jump to the 60s. Let's try this one, format synthesis using diphone concatenation. Let's listen to this example from 1968. Go to downloads, and then here, and then here. There we go. I'm going to jump right to the audio. Let's see.
By Rex Dixon and David Maxey, 1968.
The number you dialed, ME15280, has been changed.
Anyway, it's still very robotic, obviously, but the transitions are a little bit better with that diphone approach. Let's take a look at one more, maybe. Let's just jump down to 1985. Bell Labs. I think I had this already downloaded to my hard drive from before the video. This one right here. Go over here. Let's look at it.
This paper will give a brief overview of recent text-to-speech work at Bell Laboratories.
You can see they're dealing with prosody there. There's a little bit of prosody, a little of following the intonation at the end of that one. But it still sounds very robotic, right? These are legacy systems, or a historical overview of what has happened in this field. State of the art. Well, let's take a look at state of the art with Google's Tacotron. Here. This is from March of 2017. Let's listen to this example.
Generative Adversarial Network or Variational Autoencoder.
Awesome.
He reads books.
Awesome. Let's jump down to, let's try about November of 2020. Let's listen to some of these.
Talib Kweli confirmed to All Hip Hop that he will be releasing an album in the next year.
I mean, that's really good. It sounds nearly human, right? Let's see. Let's jump down to the most recent one here at time of recording. Residual adapters for few-shot text-to-speech speaker adaptation. Listen to example.
Vainly, he cast about once more for the ashtray that wasn't there, and then, in a moment of utter unthinking, he flipped the butt into the sodden air.
That's astounding. That's super human-like. I mean, it sounds like they just had a human record it, right?
Haynes came from Mentone Girls Grammar School in Melbourne, where she...
Anyway, it's astounding how much they've progressed with TTS systems just recently. Nuance has an interactive demo, which is kind of fun. This is a company that sells their service, but they have an interactive demo right down here. So let me zoom in a bit on this. So let's have Zoe, English, United States. Let's have her read something else. Let's say or let's see how she handles my Danish middle name. My middle name is a Danish last name. And I teach linguistics at Brigham Young University. Let's try this real quick. I'm not a robot. Play it.
I am Earl Kiar Brown, and I teach linguistics at Brigham Young University.
Not bad. A lot of intonation, stuff happening, duration. It's kind of funny to have it purposely have an accent in another language. So if I ask it to do, let's see if I have somebody from Spain, Jorge from Spain, say this. Let's see how it sounds.
I am Earl Kiar Brown, and I teach linguistics at Brigham Young University.
Anyway. That's kind of fun to have it purposely do a voice mismatch, have a Spanish voice pronounce something in English or something like that. Anyway, take some time to look at these sites and listen to examples. I just gave you a few examples right now, but you guys should take some time to look at it, listen to it. Here's examples. A lot of systems are available, like I mentioned. Here are some early ones that are still being maintained. Carnegie Mellon, FestVox, and Festival at the University of Edinburgh. They have their festival system and FestFox. There's kind of this collaboration between University of Edinburgh and Carnegie Mellon University. OpenMary is this system here, kind of a legacy system at this point. eSpeak is an oldie but a goodie and still sounds robotic. This is what Pratt uses under the hood to do speech synthesis. Let me just show you real quick in Pratt how you can do speech synthesis. In the objects window like this, right? If you come up to new, there's a text-to-speech synthesis right there in this menu. Create speech synthesizer. And it brought it up on my other screen. Let me pull it over here. And I'll have it do a Mel 1 English America voice. And it creates this speech synthesizer object right there. And you can just play text. If I just, let me pull the thing over here. I can just have it say that.
This is some text.
You can tell it's really robotic, right? eSpeak, oldie but a goodie. Another cool kind of thing about this is that you can say to sound and have it say this, create a sound object, but as well as create a text grid with annotations. So let me do that. So it created number 10 right here, a sound. I can play that.
My name is Earl K. Jar Brown.
My name is Earl K. Jar Brown. It's actually pronounced Karen Dash or something like Karen. Anyway, I created a text grid. So if I highlight both of the text grid and the sound that it created and do view and edit, you can see it does a forced alignment. Like it gives you a time aligned for each of these phones. But again, it's the quality of this audio is not good. It's not something you put into an actual product you're trying to sell or something. But just the idea that Pratt does some text to speech is kind of cool and gives you a forced align text grid. Let's go back to here. Free TTS is an old system. Take a look at that if you like. Tacotron 2 is more recent. NVIDIA, Tacotron 2. Tacotron 2 has this system. Cilero does more than just Russian. This webpage is in Russian. It does more than that. It does English and German. I think Spanish as well. WaveGlow is another system here by NVIDIA AI. This one here, the GTTS, is a Python interface to Google Translate's TTS system. And it's super easy to use. If you see how little you have to do to use this system, let me just use it. So I'll give you a demo here of this system. Let's see. Command line interface. Yeah. Let's just try one of these systems. Let's try this real quick. So I already have it loaded up. And I'm just going to use the command line interface. Google TTS, command line interface. And then you type in what you want it to say. Let me just say something in Spanish for the fun of it. ¿Cómo estáis? In Spanish. Vosotros. And then put in the language, code, and then the output. I'll have it save it out to como.mp3 in my downloads where I'm at right now. And it goes out to Google and has Google's TTS system do it. If I listen to it now, we pull over to this screen.
¿Cómo estáis vosotros?
It's not bad. That's pretty good. Slightly robotic, but not bad. Anyway, supports a lot of languages there. There's also Python TTS X3, which I don't have on this list. I have it in the lab. Let me just do a quick demo on that for you. If I go into Python 3, import pytts x3. Let me refresh my memory. I think it's pytts x3.speak, and then you just pass it in. I am Earl. Let's see how it does with my middle name. And I teach linguistics, period. Let's see how it does.
I am Earl Jar Brown and I teach linguistics.
More robotic than Google's, right? Anyway, that Pi TTS X3 is offline. It's not going out to the internet to Google. It's fully on your computer. Anyway, quite a few systems here. Google WaveNet. It's got their system there. I think it's just a Google Voice.
Neural 2 represents the latest in synthetic voice generation.
That's really good, in my opinion. Amazon's got Poly. You can get started with Poly there. Microsoft Azure has something here. Try it for free if you like. Mozilla's got a TTS system. Here, Mozilla TTS, you can take a look at this as well. Beyond Words AI, I think this is a service.
AI voices that do your words justice.
Our text-to-speech platform puts the latest AI voice technologies at your...
Pretty good, especially the female voice seemed pretty solid. Real quick, so Festival, like I mentioned, is an oldie but a goodie. Well, yeah. It's university, made at the University of Edinburgh in Scotland. Like I mentioned, has one of the best grad programs in speech processing and speech synthesis. It's open source, multilingual, multi-platform, and you can consider it a black box and just simply use it. Or because it's open source, you can look at all the architecture and do what you want with it. Has an API as well as an interactive shell and a command line interface there. Has documentation. And FestVox, related to Festival, enables building new synthetic voices. You can build a new synthetic voice like your own if you want. Record your own voice and create your own TTS system with your own voice. The F-Lite, the Festival Lite, is a small, lightweight system you could put on like a cell phone app or something like that. And then there's this associated resource, the Edinburgh Speech Tools library. Here is at the core of the Festival system. Great. You can do XML markup support. You can, like I mentioned before, you can do emphasis and other things. You can put in XML markup language. You can even do like post lexical rules like R insertion, like with British English or Australian English. You can hear like this R insertion, like instead of a schwa, you get an R. Like, what's an example? I can't think of an example at the moment. I have stage fright right now, apparently. Can't think of an example, but you can do different dialectal things as well. Here are a bunch of databases that FestVox uses. You can click through these. Some of these down here at the bottom are kind of interesting. These limited domain databases. Telling time, here's one about telling time. There's a student in this class in the past that created a talking clock. If you push a button on a website he created, then it would use FestVox to tell the time, the current time. The current weather condition in the U.S. Here's some resources to do that. Anyway, a lot of stuff. Great resources for finding out more. Edinburgh Center for Speech Technology Research here. All sorts of stuff going on there. Like I mentioned, they have a great grad program. This by bibliography, there's textbooks online. Here's a free textbook you can get to learn about speech processing and TTS in particular. TTS textbook here, another one. I have just, I don't think I need to show every last one of these things. But a lot of stuff. So the next lab is lab number 1 with TTS systems, is to work with 2 of the systems that I have on the lab. That's not it. Let's go back to here real quick. And lab 15. Anyway, using at least 2 of these systems to see how they do, comparing how they do, and writing up your comparison and contrast of these 2 systems that you choose. Okay, so there it is, our first lecture on TTS systems. See you next time.